All right, welcome back. In this video, I'm going to go through some examples of finding and classifying critical points of multivariable functions. The first problem here, we're given the function, and we're going to go through this recipe for finding local max and local min using the second derivative test. So step one is I'm going to take fx and fy, first partial derivatives. So the x derivative of this expression, I'm taking the x derivative of x minus 2 to the power of 2. I'm going to use the chain rule. The 2 will come down. I'll have x minus 2 to the power of 1 multiplied by the derivative of the inside. Derivative of x is 1. Derivative of 2 is 0. Plus the x derivative of y minus 3 to the power of 2. There's no x in there, it's all constants, so the x derivative of that part is 0, which I'll simplify. This is just 2 times x minus 2. We need the y derivative as well, so the y derivative of fxy, we're going to take the y derivative of the first term, the y derivative of x minus 2 all squared, that's just going to be 0, since there's no y in that part of the expression, plus the y derivative of y minus 3 squared. The 2 will come down. We'll have y minus 3 to the power of 1 multiplied by the derivative of the inside, multiplied by 1 minus 0. And we get 2 times y minus 3. Now we do step 2. Now this is going to be a little bit misleading because usually step 2 is horrible. Step 2 is to solve the system given by f sub x is equal to 0, f sub y is equal to 0. Now we don't have very much of a system inside this example. Our fx equation only has one variable in it, and our fy equation only has one variable in it. They're not coupled. We can solve each of them independently, which is nice. So fx is equal to 0 means 2 times x minus 2 is equal to 0, which means x minus 2 is equal to 0, which means x is equal to 2. F sub y is equal to 0 means 2 times y minus 3 is equal to 0, which means y minus 3 is 0, which means y is equal to 3. So we have one critical point. X comma y is equal to 2 comma 3. Now step 3, we're going to find the mixed partial derivatives. Or we're going to find the partial derivatives. I keep saying mixed. I mean all of them. I want all of them, not just the mixed one. Okay, so f double x is the x derivative di by dx of f sub x. So it's the x derivative of 2x minus 4 which is 2 minus 0, which is 2. We want f double y, which is the y derivative of f sub y. So di by dy of 2y minus 6. So 2 minus 0, which is 2. And then we want the mixed derivative fxy, which is the y derivative of f sub x. So di by dy of 2x minus 4, which is 0 minus 0, which is 0. Now step 4, we're going to construct the diagnostic function. d of xy is equal to f double x times f double y times minus f of xy all squared. So that's going to be 2. Usually these contain variables, but this time it doesn't. 2 times 2 minus 0 all squared, which is 4. Now we're going to go to the next step, step 5. we're going to evaluate our diagnostic function at the critical point. Put critical points because often we have more than one. This time we have only one, d at 2, 3. So I'm going to replace all the x's in the capital D function with 2 and all the y's in the capital D function with 3. There are no x's and there are no y's, it's just 4. D is equal to 4, which is positive. So that means it's not a saddle. Remember, the capital D function only filters out saddles. Super important point, we're not done. This is not concave up. This just means not a saddle. Now we do, did I call this step 5 and 6? I'm going to make sure my numbering is correct. Yeah, good. Okay, so because it's not a saddle, we do step 6. We check the concavity. So f double x evaluated at 2, 3. That's just 2. F double x is a constant. It's always equal to 2 at all points, including at 2, 3. So I'm just going to highlight where that came from. That just directly came from there. Didn't have to plug anything in. There was nowhere to plug it in. This is positive. F double x being positive means concave up. That means it's a local min. And now we can make our conclusion. Conclude that there's a min at 2, 3 with f of 2, 3 equals 2 minus 2 squared plus 3 minus 3 squared. Going back to the original function to get the z value, to get the height of the curve, the output of the function. So 3 minus 3 squared equals 0. So there's a min at 2, 3 is our main conclusion, and the value of the function at that min is 0, the height of the curve. Okay, this is what it looks like. This is a bowl facing up in 3D. And we found this point down there, minimum value of the function. All right, this is going to be more interesting. You can tell it's going to be more interesting whenever part of the expression in the function has a mixture of x and y multiplying together. So it's not a bunch of separate x pieces and a bunch of separate y pieces mixed together. Whenever a function doesn't have a mixture of x's and y's in the same term, the mixed partial derivative of fxy will be 0. So this is a situation where the mixed partial derivative will not be 0. It'll be something else. Anyways, let's go through the steps properly. Step 1, we're going to find fx and fy. So f sub x is equal to the x derivative of that thing. So we'll get 4y minus 4x cubed minus 0. So 4y minus 4x cubed. Now we're going to get the y derivative. F sub y is equal to 4x minus 0 minus 4y cubed. So 4x minus 4y cubed. Now we're going to do step 2, which is solve the system. This time it's coupled. This time each expression involves both variables. So we're setting the fx derivative to 0 and the fy derivative to 0. So we have 4y minus 4x cubed is equal to 0, and 4x minus 4y cubed is equal to 0. I'm going to use the method of substitution to solve this system. And the first equation, I'm going to rearrange it. So 4y is equal to 4x cubed, adding 4x cubed to both sides, and then divide both sides by 4, so y is equal to x cubed. And then we're going to take this and substitute it in the second equation, just like we would for a linear system of equations, except it's not linear, but hey, sometimes you can use the same methods. Now sub. Now x cubed, all cubed, is what we have in there. A power to a power, the powers multiply. So we have 4x minus 4x to the 9 is equal to 0. And a common factor, 4x comes out, we have 1 minus x to the power of 8 is equal to 0. Now we're going to have two different ways, two different terms that can give us solutions. Either 4x is equal to 0, which means x is 0, or x to the power of 8 is equal to 1. X to what power gives you 1? Well, x to the power of 1 gives you 1, and x to the power of 1 to the power of 8 gives you 1, and negative 1 to the power of 8 gives you 1. Negative 1 multiplied by itself 8 times, you're going to have 8 negative signs, so they're all going to cancel out, give you a positive. So we have 3 x values. We're going to plug each x value to get the corresponding y value. From y is equal to x to the power of 3. So x equals 0. We're going to have y is equal to 0 cubed, which is 0. X is equal to 1. We'll have y is equal to 1 cubed, which is 1. X is equal to negative 1. We'll have y is equal to negative 1 cubed, which is negative 1. So we have 3 critical points. Zero comma 0, 1 comma 1, and negative 1 comma negative 1. And that's only step 2. We have the other steps to worry about. So things we have to carry with us onto the next page include the 3 critical points. We're going to have to diagnose them. We're also going to have to carry with us the fx and fy. I've already forgotten them. 4y minus 4x cubed. Okay, found fx is 4y minus 4x cubed, and fy is equal to 4x minus 4y cubed. Okay, so now we're going to do step 3. Create f double x, f double y, fxy. So f double x, we take the x derivative of f sub y, or x derivative of f sub x. The x derivative of 4y is 0. There's no x in there, it's a constant. X derivative of 4x to the power of 3 is going to be 12x squared. So we got a nice negative 12x squared. F double y, we take the y derivative of f sub y. Well, let's do the mixed one next. Let's do fxy, the y derivative of f sub x. That's going to be the y derivative of 4y, which is 4, minus the y derivative of 4x cubed, which is 0. So we just get 4. And now we'll do f double y, the y derivative of f sub y. Y derivative of 4x is 0. Y derivative of negative 4y cubed is negative 12y squared. Okay, step 4. Create capital D of xy. So d of x comma y is the double x times the double y minus the mixed partial squared. So the double x we found was negative 12x squared. The double y we found was negative 12y squared. fxy we found was 4, so minus 4l squared. And then simplify. Negative times negative cancels. 12 times 12, 144. X squared, y squared, minus 16. All right, now we are going to diagnose our critical points. Diagnose critical points. From step 2. So we diagnose each one. Capital D of 0, 0 is equal to 0 minus 16, which is negative. That means it's a saddle point. We can filter it out. We can stop the analysis. Not a max or a min. Saddle point at 0, 0. Now we go to the second critical point, diagnose that one. Capital D at 1, 1. So we have 144 times 1 squared times 1 squared, which is 144, minus 16. I'm not going to even calculate what that is. All that matters is that it's positive. So that means it's not a saddle. I'm going to do step 6. After. D at negative 1, negative 1 is also positive 144 minus 16, since negative 1 squared is 1. It's also positive, so it's also not a saddle. Okay, now step 6, concavity test. So we're going to do f double x at the non-saddles. We don't need to check the saddle points. They're saddle points, they're not max or min. So f double x at 1, 1. We have negative 12 times 1 squared, which is negative. So it's concave down. So there's a max at 1, 1. F of 1, 1 is 4 minus 1 minus 1 is equal to 2. Now fyy, or fxx at negative 1, negative 1, we'll have negative 12 times negative 1 squared. Still negative, still concave down, still a max. Max at negative 1, negative 1. Then we can find the y value. F of negative 1, or not the y value, the z value is equal to 4 times negative 1 times negative 1, which is 4. Negative 1 to the 4 is 1, so we also get 2. So 2 maxima, both with the same output, both the same z value. No min. So it's a common question in a different calculus course about extrema. In 2D, can you have a function with 2 maxima and no minima? So hold on. So here's a max there, another max here. Can you have a function with 2 max and no min? Yep, you can, if there's a discontinuity in the middle. You have a discontinuity, have a vertical asymptote, you can absolutely have, and it does some weird stuff over here. like this. Maybe it just does that. So yeah, you can have functions like that, sure. And in multivariable, it's even easier because you can have a saddle point in between. This is what it would look like. The function that we went through, we found the two maxima. So x is equal to, it was -1, comma -1. This one here, +1, comma +1. And this point there is the saddle at 0, 0. So that's what the analysis told us. Two max and a saddle. Not a min in between, but a saddle in between, which is kind of a max and min at the same time. All right, here's a different format of question. And it's a lot faster. The types of problems that we just worked through take about 10 minutes each. So they're quite extensive. This type, a lot of the work is done for you. You're given a function. Sometimes you're not given the function. It's not necessary. And you're asked, what is true of some points? So you're given the function. You're given its first derivatives and its second derivatives with respect to x and y. A point could be just a random point. It could be a critical point. It could be a max. It could be a min. It could be a saddle. There's all different types of possibilities. So we have to think about what's our classification process? And once you're given a function, what do? Well, we look for critical points. Once we determine something's a critical point, we want to find out, is it a max, or is it a min, or is it a saddle? So we don't want to skip the important part of making sure that the point given to us actually is a critical point. So part 1, check if critical point. So what I'm going to do is I'm going to plug it in to fx and fy. Make sure the first derivatives are 0 there. Because that's how we found it, right? F sub x at -1, comma 3 is equal to 3 to the 3 minus 27 times -1 squared, which is 27 minus 27, which is 0. So far, so good. F sub x is equal to 0. But f sub y must also be 0 for this to be a critical point. -1, comma 3. So we'll have 3 times -1 times 3 squared plus 3 times 3 squared, which is -27 plus 27, which is also 0. So yes, it's a critical point. Now, step 2, plug into d of xy. Check for saddles. Well, what is d of xy? Let's construct it. It's going to be the same d of xy for all 3 parts of this question. d of x comma y, f double x, f double y minus the mixed partial squared. So f double x, -54x. F double y is 6xy plus 6y. And then minus fxy all squared, 3y squared all squared. Okay, so let's plug the critical point that we found into this. So capital D evaluated at -1, comma 3. So we will have positive 54 times -18 plus 18 minus 27 squared, which is 0 minus 27 squared, which is negative. 27 times 27, some big number. The negative of that, so 0 minus that big number is negative. That means it's a saddle. Saddle at -1, comma 3. I'm just going to do a double check because I'm super paranoid of that middle term, the 6 times x times y. So 6 times -1, -6 times 3, -18, plus 6 times 3, +18. Yeah, that part is 0. And by the way, whenever fxx times fyy is 0, it doesn't matter what's happening to the other piece. We're subtracting something squared. That the squaring part makes it positive, and then subtracting it forces it to be negative. But anyways, didn't take all the shortcuts that were there. And notice also we stopped with the capital D function. We didn't need to plug into f double x. It wasn't needed. Okay, next one. Check if it's a critical point. We're given a different point, 3, 1. Check if critical. Might be a trick, a dirty trick. So f sub x at 3, 1 is 3 cubed minus, no, not 3 cubed, 3, 1, so 1 cubed minus 27 times 3 squared. Right, because this says to replace the x with a 3 and the y with a 1. Gotta be careful. 1 minus 27 times 9. You can calculate it if you want, but it's negative. It's not 0, whatever it is. So it's not a critical point. 3, 1 is not a critical point. Okay. Very little work to do for that one. Next one. Which of the following is true of the point 0, 0? So check if it's critical. Both first derivatives must be 0. F sub x at 0, 0 is 0 cubed minus 27 times 0 squared, which is 0. So far, so good. F sub y of 0, 0 is 3 times 0 squared plus 3 times 0 squared, which is 0. So it's a yes on that. Yes, it's critical. It's a critical point, so it could be a max or it could be a min. Step 2, evaluate d at 0, 0. So we will have negative 54 times 0 times 0 plus 0 minus 0 squared, which is a big honkin' 0. And what does that mean? Well, if it gave us something positive, that would mean it could be a max or a min, and then we'd plug that into the f double x. If it gave us something negative, it would mean a saddle. When it gives us something 0, it tells us nothing, no information. Second partials test is useless here. No info about 0, 0. We just quit. We just give up. So that's it. That's the end. Now, in these examples, you saw how important it is to solve systems of equations. And I want to kind of tackle that in another video, and do some more examples of the full process of optimization.